Okay, now we are recording the session. And okay, I will be sharing the screen to let you know about let me see. I have so many. That's not good. I have to first. Okay. Now let me go here. Okay, you can see now the one of the topics that I placed on YouTube when I was explaining about these the type of logic gates, because logic gates are everywhere in a computer system. So when you have a box or a gate, a general gate with two inputs, these are the four possible options. In binary code, it is number 0, 1, 2, and 3. But right here in this column, you can see we have let me get this marker right here. We have the first combination. So that's, you apply these inputs and you have this output, that's an OR gate. Notice that when the NOR gate detects when two inputs are 0 and detects that with a logic 1. In other words, when they are different, the output will be 0, but only when they are 0. That's why an OR gate is known as a 0 detector. It cannot make comparisons, but it can detect zeros or 0 detection, which is very valuable in a computer system, microsequencer or microcontroller. You need to know when a counter or when some data reaches number is 0. And now we have here this output. Notice that in this output, the combination is A and not B. Sometimes I have yeah, I notice I have an error here. It has to be A, and that one is not B, so it's correct. Now, when you have, for example, this one is its output is not A, not B, and when there is a 0, I say not A, not B, and A, not B, okay, or A, not B. So you have two sum of products. There are other combinations that sometimes you don't find applications. But for example, this one is called the exclusive OR gate, or XOR gate, which detects when both inputs are different. You see, when A, not B, or not A, B, when they are different, you have a 1. When they are 0, you have a 0. When they are 0, you have a 0. When they are 1s, you have a 0. So it only detects when they are different. This allows you to make comparisons. Now, the NAND gate is this. The AND gate, which is very popular, the AND gate detects when only, it is called the all or nothing gate. So it only detects when all of them, when all the inputs are 1, okay, and you have a logic 1. When you have these combinations, the output will be 0. It's all or nothing. The NAND gate, also known as NOT AND, is the opposite. So you see 0 and you have a 1, 0, 1, 0, 1. So it's the opposite. And this is the NAND gate. So the NAND gate detects when both inputs are 1 and the output will be 0. Okay, when they are different, the output will be 1. Now there is the OR gate. The OR gate accepts when it does the sum of these two. When A or B are 1s, when A is 1, the output is 1, or B is 1, 1. When both are 1s, it is 1. So, or you can say 0 plus 0 is 0. 0 plus 1, 1, 1 plus 0, 1, and 1 plus 1 is equal to 1. Never say in this type of logic or computer science class, never say, because it happened to me in 2010. In the classroom, I said 1 plus 1, and a student say 2. It's impossible. We don't have logic 2 in binary logic. We only have a 0 or a 1, open or closed, true or false, okay, yes or not. We can't have another state in digital computers and digital logic.
Excuse me.
Yeah.
Sorry. I noticed that on 15 you ended up putting 1 5 times. Was that an error?
Yeah, no, it's 4 times, 4 times.
Okay.
Yeah, because I wrote that in my one white paper board, and I couldn't erase it. And okay, so there are only 4 ones. And another thing, the inclusive OR gate, this is the OR gate. Now the NOR gate, it is right here. Notice that the NOR gate on the first column and 14th column, they are the opposite. You see, 0, 3 ones, and now you have 1 and 3 zeros. So that's the not or NOR gate. When you have another gate is the exclusive OR, as I said a moment ago, that detects when they are different. It gives you a 1. The XNOR gate, the opposite, is also known as inclusive OR gate. This is the inclusive OR gate, IOR. The inclusive detects when they are equal. You see there? When you have 2 zeros, you have a 1. When you have 2 ones, you have a 1. So they are equal, okay? And so you have 2 types of gate, the exclusive OR and the IOR. They are very useful in designing arithmetic logic units or designing zero detections when in blocks, when you want to detect if a counter, if a loop has ended, you need those type of gates. And also the exclusive OR gate, it is used to change the polarity. So you're asking for a true condition, or you want to change that to a false condition, you use the OR gate, the exclusive OR gate. Okay. Any questions so far? I want to go through another slide. Okay.
Oh, just wanted to clarify.
Yeah.
So on the top, the line, it basically like the lines or slash B basically means that it doesn't equal B.
Yeah. When you have an A, and when you have a slash on the top or a bar, we call it a bar. That means not. That
Okay.
means this is A, and you have a bar is not A. For example, right here, this is A, and right here it is A. When you have a 0, it's not A, not A. Right here is B, B, these two, and these 2 zeros is not B. Okay. So the most basic gate is embedder, because it is the one that converts a variable into a not variable, a true into a false into a true. And that's made with, in hardware, it is made with these chips, the classical ZD4007. You cannot be an engineer if you don't know the 4007. Okay. They are more popular in the engineering field. They are more popular than Coca-Cola. And you need to know it. So this is, if you buy this chip, which by the way, we have many of them in the lab at IBC, these are embedders. So you have your input and your output. So you have a 0, the output will be 1. If you have 0 volts, the output will be 5 volts. If you have a 1, the output will be 0. Or a 1 is any voltage. The voltage can be from 3 to to 10 volts in this device, even 15 volts, but we are using 3 to 5 volts, or 5 volts is the most popular. So you have 5 volts here, the output will be 0. These two transistors called disable, they are used to create what we call high impedance, or what we call the tri-state. Okay, the tri-state inverters are used to connect data. They allow you to connect bank of memories, many memories, and you can select them, and they can share one data bus without having a conflict. If you don't use these disabled units and these disabled units, if you don't use them, there will be a conflict and the data bus will crash. So you need to disconnect, because this one disconnect. So when you are using this one, this connects the inverter. This is the inverter made of these two transistors. This one connects the inverter to voltage, and this one connects, it's like a switch, connects the source to ground. This one, the drain, this is the drain to voltage. And that's what we call low impedance. It is working as a regular inverter. But when you want to disconnect this from the power source, this one will be disabled, and this will be disabling the connection to ground, and this one disables the connection to voltage. So they will be floating, they will be in high impedance, and that way you can allow all their data to flow. You can see it as a red light in a stop, in a cross section. If you have a red light, you can't cross because there's other data flowing, other cars. You have to stop. Once you have a green light, these ones are enabled, and you have green light to flow your data. And because you are sharing the same highway, can you imagine having 20 highways just because we have 20 cars that are willing to travel to some place? No, you only need one highway, and you need 20 different cars or 100 cars, but every car will have its time frame to travel through the data path. That's why you need the classical tri-state inverter. Okay. So as I said in this lesson that I already placed there in the channel, the lesson is being recorded, right? I think I did it in the beginning. Yeah. And right here, this is an inverter. This is the symbol of an inverter. You need to know the symbols. In this class, you don't need to know exactly what is happening in the hardware, but you need to know the symbols. And this is the symbol for an inverter. So when you have a resistor, this is known as a pull-up resistor. You connect it to voltage, and the switch is open. So when the switch is open, the pull-up resistor creates a logic 1 right there. And that's why you have a logic 0. Okay. When you press the switch, you create here as 0, and the output will be 1, will be 5 volts. When you release the switch, the resistor pulls up this wire to voltage, to VDD. That's why you see here this signal going up again, because you release the switch, and then the output goes back to 0. Okay. So pull-up resistors are required to avoid having the inputs floating and creating noise. You have electrostatic charge in your body. If you with your hand approach this device, it'll be oscillating, and it'll be creating high frequency noise in the range of megahertz. And you don't want that to happen. That's why you need the pull-up resistor. That way you define that the wire is never floating. It's always tied to voltage. If you want the opposite to happen, like when the switch is released, you want a 0 like here, you have to place a pull-down resistor to ground, and the switch here. So it is open, you have a 0 because of the resistor, the pull-down resistor. And right here you have a 1. Now when you press the switch, you apply a voltage, and the output becomes becomes 0. When the output becomes 0, this current flows. Okay, the current flows because you have a 0, and 0 means ground, and you're right here you have 5 volts VDD. So the current flows and the LED glows when the switch is pressed. When you release the switch, like in that state, when you release it, there will be a 0. There will be a 1, so 5 volts will be right here. And because you have 5 volts here and 5 volts on the other side of the light emitting diode or LED, you have 5 volts and 5 volts. The LED doesn't have a voltage, so then the LED will be off. I always ask this question: have you ever? Well, everybody has seen, but have you ever seen birds on the power cables? Mounted on power cables? You see them in the morning.
Yes.
Yes.
Yeah. Why they don't get electrocuted? Why they don't get an electrical shock?
Is it because they're not grounded?
Yeah, because with both of their feet, with their both feet, they have, let's say the line is 13,000 volts or 70,000 volts. In his right feet, it has 70,000, and on the other one, 70,000 volts. So the bird is not having any voltage. 70,000 minus 70,000 is equal to 0. It's not grounded. He will never, those birds will never be electrocuted. But as soon as there's some rainwater or breeze, fog, and the fog is very dense and touching ground, the cable will spark the ground. And that's why sometimes in the winter, you see in the fog on those power cables, you see some like electrostatic charges going from the pole to ground or going from pole to pole. I've seen those arcs traveling on the wires. Have you ever seen that?
Wait, so if the water were to touch you, do you get like a shock, or it just loses its energy over time?
No, the water is conductive. Many people did that, and and they're not here.
Oh, okay.
They died. No. It's what I'm saying is the water vapor, the fog. If the fog is very dense, it'll act as a wire, as a conductor, and the electricity will travel through the fog if it is very dense. Okay. So and as I said there in my video, of course I decided to have a live lesson on this, not just the video, because sometimes you ask me questions that you can't do it on the YouTube video. Okay, this is the symbol for the NAND gate. Okay, notice that there is a circle there. If you attach both inputs, that's an embedder. Okay, so you don't need to buy another chip, the embedder. You just tie both inputs in the NAND gate, and the output will be 0. Why? Because you're tying these two, and you only have these two states. When there is a 0, there is a 1. When both inputs are 1s, there is a 0. So that's an embedder. This is your input, your output, your input, your output. You can have those combinations because you tie these together. They can be different. They have to be equal. And that's why you have an embedder here and an embedder there. If you need an AND gate, you just add an embedder. You put it at the end, at the output, and the NAND gate will become the AND gate. So the AND gate, notice when both inputs are 1, the output is 1. So all or nothing. That's the AND gate. The NAND gate is when both inputs are 1, the output is 0. Okay. And when you need another way to make the OR gate, you can make an OR gate. So you can make more combinations. I don't want to get into details in Boolean algebra because this class is not a Boolean algebra or digital logic. It's just an introduction. You might be wondering, where can I get a NAND gate? This is a classical NAND gate. So there are 4 in a single chip. You can buy those devices for 20 cents, 25 cents. And you have 4 NAND gates. And you can do a lot of stuff with this. This is the voltage pin. This is the ground pin. Okay. So you have to apply 5 volts and ground to use them. When I was studying electronic technician and I purchased my first gates, the professor never told me that I had to apply power. So I was applying voltage here and the LED never glowed. And I asked him, what is happening? First question was, did you apply power to the chip? You never told me. So, okay. So no excuses. I told you, you have to apply 5 volts and ground, and then you can use them. These are another applications of NAND gates, not too related to this class. Okay, this is a good one. You need the AND gate directly. This is the device you have to buy, the CD4081 or the 7408. There are many types of technologies in gates, of course. CMOS technologies are the best technology. They don't consume power. Your cell phones, they use CMOS technology. You probably remember the cell phones in the early 2000s. They were consuming, they were only operating by, they could only operate for about 5 hours and they were gone because they were using other technologies, not exactly CMOS. And you want to make a 3-input AND gate, if all or nothing, if the 3 inputs are 1, I need an output equal to 1. You see, all the other combinations, you get a 0. Okay, I'm still having students arrive into the classroom, no problem. Anyway, the session is being recorded, so you can watch it, the previous material later. So you have a 3-input AND gate. The output of the first gate, you have to connect it to the second AND gate, and now you have 3 AND gates. 3 inputs to create a 3-input AND gate. If A and B and C are equal, are 1s, the output will be 1. Okay. For any other combination, it will be 0. And you have to say this. If A is false and B is false and C is false, the output will be false. If A is true, B false and C false, the output is false. If B is true and the other 2 false, you see, that's the way you have to say it. If A is true, if A and B and C are true, the output is true. The output is 1. And this is how you write the equation. There are other combinations that you can make by attaching AND gates. Okay. By attaching the input, the output. This is Boolean algebra. As I said, I don't want to get into Boolean algebra in this class. By the way, I said that if most of you are interested in IVC to teach you a class, for me to teach you a class on digital logic, which is gates, Boolean algebra, K-maps, and a lot of stuff, you have to request that class to my boss. The class is called ELTR 240, Electronics 240. You have to request it, and if my boss receives a letter with minimum 15 signatures, I can teach you that class in the summer or in the fall or whenever you can. If you are interested, the class is here. And believe me, that class is quite interesting for those of you getting a career in computer science or mechatronics, engineering, mechanical engineering, aerospace engineering. Another thing is the ORNOR gates. As I said a moment ago, the OR gate is A or B, you see. When 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is equal to 1. So you have here the OR gate. You do the opposite, it is called the NOR gate. This is the symbol for the NOR gate because it is the ORNOR. And you see a circle right there. If you attach both inputs, you get an embedder. Because when you have both inputs are zeros, you have in the NOR gate, you have a 1. And when both inputs are 1s, you have a 0 right there. So that's an embedder. And those are the combinations you can make. If you attach this one, x is equal to x. And you might say, and why, you might want to say, you might say, or you might be asking yourself, what is the purpose of having the output following the input if I have an x here and an x there? Because many times you need the output, the input, this variable x, you need to have a high impedance and with a low impedance right here. That means that you can drive other devices. So you can use it as a driver. Same here. But here, it doesn't matter what you apply here, the output will always be 1 or 5 volts. And if you attach them together, also you have the input, the output follows the input as a driver. And also here, another application. Okay. And the exclusive OR gate is one of the devices that it is used a lot in computer science and computer architectures. The exclusive OR is used to compare if two bits are equal or not. Okay, so look at this. If they are equal, you have zeros here. You have a 0. If they are different, you have a 1. You have ones, you have a 0. In the IOR, if they are 0, you have a 1, you have a 1. If they are ones, so if they are equal, the IOR allows you to do that. If they are different, you have this result. That's good. So this is how you can make a exclusive OR, or you can buy it. The classical numbers, you want to buy these chips, is the 4070 and the 7476. Okay, those are the two classical exclusive OR gates. You will not find IOR gates. You have to make them. Okay, how you make them? By applying an embedder at the output. Okay, and one of the most important features of the exclusive OR gate is how to change the polarity. So you have an input here called, let me amplify this a little bit. Okay, you have an input here called X. Your output, if this is 0, you see that? Well, but your output will be not X. But this is the IOR, so we don't want to use the IOR at this moment. We use the exclusive OR. So a 4-bit comparable with exclusive OR gates is made this way. So a 4-bit comparable with XOR gates. So if you have 4 inputs, 4 bits, and remember in computer science also, 4 bits is called a nibble. I didn't say evil, a nibble, or probably a nibble, a nibble. And 4 bits are called, in this case, A0, A1, A2, and A3. The other bits coming from another data, another nibble, are B0, B1, B2, B3. So you need to compare them. You need to know if A is equal to B, where A is 4 bits and B is 4 bits. So the exclusive OR gate will tell you when they are different, but you want to know when they are equal. So you apply an embedder and you will know when they are equal. So when you have one here, one there, and another one there, 4 ones, 4 bits equal to 1, 1, 1, 1, 1. The AND gate will tell you, because I have 4 ones, my output will be equal. My output will be equal to logic 1. That meaning that they are equal. And you can have 16 different combinations, 16 different equals. Okay, when 0 is equal to 0, when 1 is equal to 1, up to 15 equal to 15. Okay, but of course, because you have 8 bits, you have 2 to the 8 combinations. That means 256 different comparisons. Okay, 256. And from those 256, only 16 of them will be equal. That meaning that 240, 239, 240 will be different. And the speed is high. So in nanoseconds, you will know the result. So you want to know if A is equal to B, that's how you write it in assembly code or C language or any other language. And on the right side here, another way to do it is with the NOR gate. Because when you have 4 zeros, the NOR gate will respond. If I have 4 zeros, the output will be 1. Now, you see here I have one stage that takes 10 nanoseconds, another stage that takes 10 nanoseconds, and this one. So I have 30 nanoseconds. In this one, I only have one stage that consumes 10 nanoseconds, and this gate that consumes 10 nanoseconds. Which circuit is faster? The one on the left or the one on the right?
The one on the right.
20 nanoseconds. And remember, you might be thinking, and why should I care about a nanosecond? Because 1 nanosecond is 1 gigahertz. If you say 1 nanosecond, you are increasing your speed by 1 gigahertz. So you say 10 nanoseconds, you are increasing your speed 10 gigahertz. That's why it's important. Don't say, oh, I don't care about how many stages. No, you have to care. You have to be aware of that. And I'm giving you a 10 nanoseconds because that's a standard propagation delay. Of course, there are other gates that have 5 nanoseconds, 4, 3, even less than 1 nanoseconds. They are now working in picoseconds, 10 to the negative 12. Now, making XOR gates with NAND gates, that's another option. But if you don't have NAND gates and you're not gonna be complaining, oh, I have to go to Amazon and design and request a XOR gate. It's gonna take 3 days, 4 days to repair this thing, this board. No, you can make it with 5 NAND gates. You just make those connections, and here is a Boolean algebra to demonstrate that you have a XOR gate. When they are different, look at that. When they are different, you will get an output. This is why it's interesting to learn Boolean algebra, because you have other solutions. Sometimes this is what I call, this is what your mama never told you. You see, digital computers, and they are fun. You have to love the subject. Truth tables logic circuit, that's a topic that is related to digital logic, not to this class. K-maps is another topic. Karnoff maps. They are, every engineer needs to know K-maps, but it is not the topic of this class. So I have to skip it. Okay, and that's another topic I placed in the YouTube channel. Multiplexers or data selectors, channel selectors. So sometimes I have still the picture with the Spanish titles. Don't worry. Anyway, the symbols are the same. And I think I place a different pictures in your in your YouTube lesson, because I had to make these designs again. I have to draw them again, take pictures with the titles in English. So you have here a multiplexer and with 4 inputs, A, B, C, and D. And this is the output. Okay, so you want to select the output when the output is equal to 1. Okay, so you have the selector input. When both selector inputs are 0, the channel I will be getting on the output will be channel A. Look at this. So when S0 is, when I have not S0 and not S1, in other words, when they are zeros, like this, channel A will be transferred. Channel A will be transferred from here to here. The other case, when I have S0 equal to 1 and S1 equal to 0, or I have S0 and not S1, channel B will be transferred. There it goes, channel B. I can't have 2 channels at the same time. That will be a conflict. It will be like having 2 cars in just a single highway, one directional highway, narrow highway, and 2 cars facing each other. It's a crash. That's impossible. Same thing here. Now, when you have not S0 and S1, when they are in this way, you will get channel C. Okay. And when both inputs, channel selectors are S0 and S1 are 1s, you will have channel D at the output. So only 1 channel at a time, not 2 channels at a time. Only 1 can be selected. So it's multiplexers or maxes. We call them as maxes, a max, 4-to-1 max. And this is a 4-channel. This is a 2-channel. This is the most basic one, the one on the right side. You have channel A, channel B, and the output. So you just tell when select channel A when selector is 0, and or select channel B when selector is 1. So this option or this option, never both at the same time. And they are specified right here. Okay, and this is a circuit. With these equations, when you take digital logic, you learn how to convert these equations, Boolean equations, into a digital logic circuit. There are some compilers for field programmable gate arrays or programmable logic devices where they ask you for the equation. You enter the equations, the compiler converts this to this circuit, and then you have the chip ready to work. Those are called PLDs, programmable logic devices, PLDs. And that's another topic you will learn in your engineering career, PLDs. And now they call them CPLDs, complex PLDs, complex programmable logic devices. Okay, and another 4-bit selector, you have 4 bits here, in channel A, 4 bits there, 4 bits for your output. So you can select 2 nibbles. One nibble is here, another nibble is there, and this is your output. Okay, so you have 4 outputs because you have the 0 bit and the 3rd bit, so 4 bits. And you can also make it an 8-bit, so you can have a byte selector. You can select this byte or another byte. Remember, 1 byte is made of 8 bits. This is a chip AC159. Any questions so far? Okay, there are other applications like using a mux as a logic gate. If you don't have gates and you want to get an AND, NOT, and NAND gate or gate, exclusive OR gate, you do those combinations, you will get a gate. You don't have to buy one. So a multiplexer will save you from many having to buy many chips. The demultiplexers are the opposite. When you want to send an input to a different source, to another, for example, you have this data and you want to send it to memory A, or this data, you want to send it to memory B, to another bank of memory, you need a DMUX, a demultiplexer. Now you have this data and you want to send it to memory A or memory B or memory C or memory D, you need a DMUX, a 1 to 4 DMUX, demultiplexer. Okay. Decoders are interesting because decoders are used to decode instructions. And probably the word might sound not too familiar for all of you. What is a decoder? How can I decode an instruction? And instructions in a computer, they need to be decoded because they come in binary code. So you need to decode them to send data, to control the data flow inside a microprocessor. Okay? Don't forget what I said. They are used to control the data flow inside a microprocessor or microcomputer, microcontroller. The data flow, where will you send the data? Using a decoder. And the decoder will control a multiplexer. Okay. So two input, 4 output decoder is like this one. You have 2 inputs, A and B, and 4 outputs, X0 to X3. And you see, you want to have this output when both inputs are zeros. If they have, you have 0, 1 in your inputs, you want to X1, just that output to be logic 1, the rest will be 0. And you have 1, 0. Right here, you have this one equal to 1. And you have both ones, A and B. X3 will be 1. That's what a decoder does. This is these are the 4 equations. This is the circuit from those equations. It can be done with a PLD. PLD can perform it. Now there is a even higher decoder, 3 to 8. You have 3 inputs and 8 outputs. Notice how depending on the combinatorial logic right here, you have these or these outputs. Well, I'm sorry for that. I can't erase it. And also here you have this one and this one. So you see the diagonal, all the ones in that diagonal is because you are controlling which one you want to be an output. So you are decoding. That way you can control the data flow. This is the circuit made of 3 embedders. Notice how when you have an embedder, this is C, this is not C, this is B, not B, A, not A, just because the 3 embedders. Then you do the connections to AND gates and exclusive OR gates. This pole is called that way because controls polarity. It changes the logic from true to false or from false to true. Okay. And those are other decoders inside the chips, a classical decoder to 7 segments in a display. Because you convert this code, this decimal code, BCD code, binary coded decimal, into 7 segments or a single digit. I don't know what happened here. Okay. Any question so far about this? I want to change the screen. You know what? I'm going to give you a 5-minute break. You can drink water or whatever while I am changing the screen and otherwise. So let's take a 5-minute break because today we will stay here till 5:30. So probably half an hour or 40 minutes more. Take a break and I'll be here. If you have questions, you can ask me. Are you there, Kevin?
Yep. Sip.
Get ready, because one day in the future, you will be teaching this class.
I hope.
Hopefully. Okay. I just I have to go to my, okay, the micro sequencer. The Adobe, it's not working. It couldn't handle so much files, too many files. I have to close this. Notice that this is a computer, a laptop IBC gave me 2 years ago, and it can handle all this memory. The thing is that I opened it up, many files in the Adobe, and it crashed. It couldn't handle the priorities, interrupts, and the memory. Well, what I'm going to do, I'm going to open those files separately in another file, which is, don't worry. I'm closing many files. That way, my computer will be working better. Okay, now I'm going to open a new file, but no, it doesn't let me to go here. No, computer got crashed. Okay, this is what's happening. The Adobe Reader got crashed, and it doesn't allow me to get into other files, nothing. So I can't access my other files. So no problem. I think we saw good material today. It's a review of what I placed in the YouTube channel, the YouTube lessons. But I'll be so I will meet you on Thursday to see the micro sequencer as an introduction to the microcontroller. And I will not open so many files because that's what happens to this computer. In the meantime, so that'll be all. And tomorrow or later tonight, I will be giving you the link to the Thursday Zoom meeting at 4 p.m. And in a moment, I will stop this recording. So students, I'm gonna stop recording right now.